So our first speaker today is Sylvia Hannah from Northwestern University. Her field is inorganic and materials chemistry. Her advisor was Omar Farha. She actually spent her practicum in 2021, interesting year to spend a practicum, as I'm sure everyone remembers, at Sandia National Laboratory. And I'm making sure I still have the correct title, identifying energy structure property relationships in uranium metal organic frameworks through their dynamic crystalline structure transformation. Breathful. So Sylvia, the floor is yours if you want.
Okay, thank you so much for the introduction. It's really a pleasure to be here. My name is Sylvia Hannah. I was a fellow with SSGF. And I recently defended my PhD in January of this year at Northwestern University in chemistry in the Farha group. So none of the research that I'm going to be telling you about today would have been possible without the support from the SSGF and from the fellowship community and the different experiences and opportunities. So definitely a big thank you for that. Okay, so before I get into the technical side of this research, I just want to address a little bit about how it's really important for today, because I remember being a first year SSGF it was challenging for me to kind of relate how my research technically was super important for stewardship science. So if you know this, you can tune me out for the first slide and then jump back in on the next one. But a lot of this really starts with the history of uranium. In 1942, we saw uranium in the Manhattan Project used in nuclear weapons, and then in 1951 in the first nuclear power plant, generating usable electricity. And then finally in 1963, the Nuclear Test Ban Treaty ushered in this era of stockpile stewardship, which still exists today, and that we are all part of. And all these processes are really tied to uranium enrichment, which is essentially when you can concentrate the uranium-235 isotope, and then you can also end up with a concentrated version of the uranium-238 isotope. And so these are enriched and depleted uranium, which can be used for different things. So for example, enriched uranium we use in things like nuclear weapons and nuclear power, and then depleted uranium gets funneled into things like bullets or radiation shielding, as well as research, which is what I used in the labs at Northwestern. So with all this information in mind, there are some general themes or questions that surround uranium in society today. So first of all, we still have a lot of nuclear waste present from the Manhattan Project, and so one big question is, how can we remediate this nuclear waste? As nuclear power becomes more and more popular, there's also the question of how can we use depleted uranium, which results from uranium enrichment process. And then finally, how can we effectively steward this stockpile, which was just really talked about in detail in the previous talk. So even though we have these really big societal questions, the good thing is that we can answer them, or try and address them at least, with scientific solutions. And so in the research that I did in grad school, I tried to use uranium chemistry and really understanding the fundamental chemistry of uranium through nanoscale materials to help answer these questions. So what really is a nanoscale material? Most of you probably work on the nuclear level, not so much on the nanoscale level. So we're going to get into that a little bit first of all. So let's start with something that everybody knows the size of, Great Pyramid of Giza. That stands tall at 10 to the 11th nanometers. We can get smaller and smaller until we get all the way down to a red blood cell at 10 to the 5th nanometers. And then here we are. This is a shout out to my 2021 experience at Sandia. We have the COVID-19 virus at 10 to the 2nd nanometers. And this is the area of space, the size that I'm going to really be talking about today. And the nanoscale materials that I used in my research are called metal organic frameworks, and they're essentially just tinker toys, but on the nanoscale level. So these are comprised of inorganic nodes and organic linkers that self-assemble into these three-dimensional, tunable, porous materials. And these are pretty much these smart and programmable materials because they are so tunable. So for example, you can have a host of different node topologies and node identities with different metals that you can then mix and match with different organic linkers. And here I'm just showing you a really small selection of organic linkers. But you can mix and match both of these different building blocks to make a host of different metal organic frameworks, or Moths. And you can imagine these have different topologies, different pore sizes and shapes. You name it, you can get it. So Moths in materials science are known for a variety of different attributes, but their most popular one is probably their surface area and their porosity. So what that means is if you have just 1 gram of moth, which is about the size of an M&M, it holds the surface area of an entire football field. So that makes it really useful for different applications. Like in my group, something that we've worked on is putting moths on different clothing for detoxification of chemical warfare agents. You can also use it to store and separate gases like CO2, and then even harvest water from the air in different desert climates and environments. But in my research that I'm going to be showing you today, I'm using moths for a much more fundamental aspect. And so here I'm using moths to harness uranium chemistry and address these 3 fundamental questions that I brought up in the first slide. So first of all, how can we use moths to remediate nuclear waste? Something you can do is actually use uranium-based moths to recycle them and capture radioactive waste with them. So these types of porous materials, for example, zeolites have been used in like the Fukushima disaster to capture radioactive waste in a similar mechanistic fashion. You can also use moths in the second question here, applying depleted uranium. So with a lot of the applications for depleted uranium, you need uranium in low oxidation states like uranium +5. And what happens is when you have 2 uranium +5 ions, they'll kind of bump into each other, share electrons, and then you're going to end up with different oxidation states than what you originally wanted. And this is called disproportionation. But what moths allow us to do is really anchor uranium ions at those node sites and prevent them from bumping into each other, disproportionating, and we can really harness its chemistry. And then finally, effectively stewarding the stockpile in this sense allows us to look at fundamental structure-property relationships. And so when you have uranium in a moth like this, you kind of have the best of both worlds. You have a solution state and a solid state type of material where you can really harness that hybrid aspect to learn about isolated uranium atoms and coordination effects. And so this third point is kind of what I'm going to tell you about today, although I have looked at really all these types of different things in my thesis research. So structure-property relationships are well known and understood in all of material science. You want to understand structure-property relationships to understand your material. But I kind of wanted to take this a step further and look at not only how structure produces function, but why structure produces function. And to do that, you have to look at one more aspect of this, which is energy. So my thesis research was looking at energy structure property relationships in these uranium-based moths. And so I'm not going to take us through all of these, but these are the different types of aspects and stories that I looked at in my research. I'm just going to focus on the culmination of the research, really looking at energy structure and property relationships in one of the last chapters of my thesis. So we're going to go through a story here with all these different parts, and we're going to start off with the background of this story. So to understand this research, we have to first talk about some definitions. So example, entanglement. So entanglement is when you have multiple rings that intertwine with each other such that the only way to separate them is to break one or more of them. And some common examples of this are things like the Olympic rings or the keys on your keychain. And some less common examples are things like chainmail or optical illusions that are really just entangled rings. So if we look at this at a more chemical level, we can see that going from a material that is non-entangled to entangled is actually very energetically favorable. And that's because you end up having these non-covalent interactions that favor your entangled material. So things like pi-pi stacking or hydrogen bonding are really going to favor this type of a material over a non-entangled. And that's why entangled materials are ubiquitous both in synthetic systems and in nature. However, if we look at the pore space of these materials, you can see that the non-entangled material actually has a lot more accessible surface area where we can do a lot of interesting and useful applications in chemistry in, whereas we have this confined pore space in the entangled material. So what we really want is to reverse this reaction. Oh, well, sorry, here we go. I forgot I had this animation here. Here are some examples of the enhanced function that you can use these pores for and how we'll end up getting reduced function in this other case. But what we really want is to reverse this reaction so that we can favor this open material and use it for these types of applications. The problem is that to reverse this reaction requires some sort of energy input. So things like temperature, solvent, pressure. And that takes time, money, effort, things that we don't really want to necessarily spend. So the research that I'm going to show you today is about a phenomenon I discovered called charge point-point repulsions, which really allows us to reverse this reaction, makes it very useful for different applications, and also teaches us a lot about what uranium can do, as this is a discovery that we haven't actually seen in any other type of metal organic framework based on any other type of material or metal aside from uranium. So it teaches us a lot about uranium's chemistry and how it can behave under extreme conditions like aging. So getting into the discovery itself. So I made this metal organic framework based off of this uranyl node here. It's a uranyl in the +2 oxidation state bound to these three equatorial linker groups. And here's what my linker looks like. So for those of us who aren't really a big fan of chemical structures, we can just use these types of building blocks to represent the types of building blocks that I'm showing up here. So this tritopic and this ditopic building block are going to self-assemble into this three-dimensional material. So this is a Moth that I named NU13036, and NU is for Northwestern University. We're really fun. We name all of our Moths after our university. Super original, I know. But you can see the pore size of this Moth is it's a little cut off, but it's almost 40 angstroms. But what I'm showing you here is a very simplified version of this Moth. It's actually 6 of these identical networks entangled together. So in Moth speak, we call this a 6-fold interpenetrated Moth, where the diameter now of the pores within the Moth are about 15 and 20 angstroms. So this is a single crystal structure, and after making my single crystal structure, I wanted to make sure that the bulk powder that I made also really matched up with the characteristics of my single crystal. So I ran what's called a nitrogen physisorption isotherm, which is essentially where you take your powder, you dose in a fixed amount of nitrogen gas to your powder, and you monitor the uptake of that gas into your powder on the y-axis. And what that tells you is a lot about the internal pore shape of your Moth. You can extrapolate this data to what's called a pore size distribution, which shows you that I have 15 and 20 angstrom pores. And this matches up really well with what my single crystal structure showed me. But I put this project aside for about 5 months. I started working on another project, and I came back to this material, which I had left sitting in my fume hood, and I ran the exact same experiment to start off on the exact same batch of material, and I saw a really different result. So even if you're not familiar with isotherms, you can see that the shape of this isotherm is super different, and we have a pore size now at 40 angstroms instead of 20 and 15, which clearly does not match up very well with what you would expect. So this, however, does match up with what the non-interpenetrated pore size looks like, about a 40 angstrom pore. So this was the first of several clues really showing that there was this transformation from this densely interpenetrated structure to a much more open structure. And so going forward, I collected single crystal structures of this process as it was occurring. You can see this is a version of the 6-fold, a 3-fold, and then a completely non-interpenetrated Moth. So it's really cool to get to capture this in real time and see that this structural transformation was actually occurring. But what's more interesting is that this final non-interpenetrated material actually holds the record for the highest porosity of any Moth that's been reported, where you have over 96% of its volume being totally empty. So that really begs the question, how are we getting this super open material from a material that was originally really densely packed when we know that this process is reportedly not favorable? So I wanted to understand what the driving force for this process was. And you can understand the driving force by going a little bit more deeply into the structure. So throughout the structure, there are these 2 different motifs that repeat, where you have these uranium nodes, each of which have a -1 charge on them, and they're separated. So these are nodes on different lattices throughout the structure, and they're separated by a pretty short distance, 9.7 and 8.1 angstroms. And so these reminded me a lot of like 2 North Pole magnets. If you put 2 North Poles together, they're going to automatically want to repel each other and go further and further from each other. And so I hypothesized that these charged points were repelling each other in space and driving this disentanglement process. And we term this charge point-point repulsions. And so to see if this hypothesis could be correct, I collaborated with the Gagliardi group at University of Chicago. And we did what's called an energy decomposition analysis, which is essentially where you take your motif here, your two different nodes, and you pull them apart. And as you pull them apart, you measure their interaction energy along this uranium-uranium distance. And here in this bottom of this well, you can see is the most favorable energy conformation. But what's really interesting here is that throughout this entire interaction energy diagram, you can see that all of the energies are positive, which means that they're all repulsive, really supporting the idea that these charged point-point repulsions are what's driving this disentanglement. Taking this a step further, we also modeled the free energy of this transformation using this equation here, which I won't get into too much of the details, but you can see the important point is that the free energy of this transformation is -15, which is a pretty significant value, showing that this transformation is actually completely spontaneous and happens pretty much on its own without some sort of external stimuli. So then I actually noticed something really interesting in this process as I was monitoring it. I noticed that during the cold weather in Chicago, D interpenetration happened really quickly, whereas when it was super hot and we had humidity, it happened a lot slower. So this showed me that water must have been playing some sort of role in this transformation. So I looked a little more deeply at the structure, and what I saw from the single crystal structure actually was that there was a water molecule hydrogen bonded between these two nodes in the interpenetrated structure. However, we know that these charged point-point repulsions are also happening, and so you can deduce from this that there are these two competing interactions, one that holds the 6 networks together and one that forces them apart from each other. And so at the end of the day, we see that this non-interpenetrated structure results and these charged point-point repulsions win. You can also calculate this looking at the free energy of this transformation in the presence of water, which is kind of fallen off of here, but it's the blue trace you can see is less favorable than the red trace here. I also did an experiment here to show that this could be possible. I removed water from my reaction conditions and was actually able to speed this up by 36 times and get D interpenetration in 4 days instead of 5 months, just by showing that these competing interactions really do occur. So I got a 5-minute warning, so I'm not going to go into this last point here. We're going to skip through it, but this is an experimental control to really show that charged point-point repulsions are happening. You'll have to talk to me after for it. We'll just jump into the final implications of this work. So here, for the first time, I reported this spontaneous network disentanglement that really swaps the energy landscape from what's typically accepted in material science, at least, where we can get this open material that's now energetically favorable through these charged point-point repulsions of uranium. And what this shows us is how energy, structure, and properties are all related here in this type of a story, and how you really need one to understand the other. It's also showed me a lot about how uranium can act as a very different type of metal compared to other ones that we typically put in Moths, and how it behaves under aging conditions. So I'd like to thank a lot of the folks who were instrumental on this work. This is my PI, Omar, our group. These are all the different collaborators I've had during my PhD, and different collaborators from my group as well. I'd like to thank the funding that made this all possible, and then finally the SSGF family for everything that has happened over the past 4 or 5 years. I'm thankful for the friends that I've made through this. Special shout out to Chris and to Shelley, as well as all the other people who've been so instrumental in this fellowship, making it come together every year. And then, as was mentioned earlier, I did spend my time during my practicum at Sandia. So I'd like to shout out to my mentor, Tina Nenoff, also Matt Gomez for his support during the entire process. He's also a alum of this program. And then to Susan and Jess, who are also mentors to me while I was at Sandia. So with that, here are some pictures of the crystals that I was able to make in grad school that I really love, and I'm happy to take any questions that you might have.